It's thinking, it's thinking, it's thinking. And we're recording. Sweet. Okay, let's knock the rest of this out. So coenzymes. We're talking about coenzymes. So coenzymes, we're going to see they are the larger, more complex organic molecules. Or they can also be like, they call them metallo-organic. It just means that they have metallic parts inside of them as well as the organic, like the carbon base. The main ones that we're going to talk about, especially, are vitamins. Actually, you know what? Before I get too much further, because I'm kind of answering the next question and kind of skipped this actual, what this question is. The actual role of cofactors and coenzymes, they perform the exact same function, and that is, first and foremost, they activate the enzymes. We need cofactors and we need coenzymes in order for the enzymes to work, okay? Some vocab for us. So cofactors and coenzymes bind to, this is a vocabulary word, apoenzymes. This is the inactive form of the enzyme, to make it a hollow enzyme, and that is its active form. Okay. Cofactors and coenzymes also help with group transfer reactions. So we think about like our functional groups. That's what we're talking about, functional groups. And then I also have, as a side note, is also they can function as a co-substrate or a second substrate, meaning that they get consumed during the reaction. Okay, means that they get incorporated into the stuff that's the substrates that are interacting, and they become part of the product. And another, just while it's on my mind as well, another addition to the defining of enzyme, part of what makes an enzyme is that it is the same before and after the reaction has occurred. It does not get used up or combined with products. So you should see, if you see a chemical reaction and the enzyme is not on both sides of the equation, or it's like it's not still the same, if it was absorbed at all and became part of the products, it is not an enzyme. Okay? It has to be the same before and after. Okay, back to vitamins. So the big thing I want you to remember here, and that you will be really tested, you'll be tested on a lot of these, are your B vitamins, okay? B vitamins. The ones that we need to know are 1, 2, and 3, 5, 6, 7, 9, and 12. Okay. These ones, there's a mnemonic that to help me remember it, it says, that is tall, rich, nudists, played, pickle, ball, or centuries. Okay, and this stands for our B. We have B1, B2, B3, B6, B7, B8, B9, and B12. B1 is our thiamine. R is our riboflavin. B3, tall, rich, nudist, is our niacin. You'll see that when we talk about NADH, NAD+, NADH, NADHP, all of those fun stuff that we'll see that throughout biochemistry is niacin. All reduces play. Let me pull up to make sure get 6 and 6 mixed up. Make sure that I spell it all right. There's a lot of them. I want you, and I want you, and you. When you're preparing for boards, this is what you'll see. Something like this. All of the good stuff. Thiamine, riboflavin, niacin. Oh, I missed B5. B5 is pantothenate. B6 is pyridoxine. 7 is our folate. Nope, I lied. B10 is biotin. Pickleball. Wrong. B9 is our folate or folic acid. And B12 is cobalamin. These are never going to go away. So please, 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 I did not learn these very well my first time through Biochem 1. Trust me, please, please, please know these. Put like 8 million stars next to these, because if you memorize these now and know these like the back of your hand, these come up in like 4 or 5 different classes, and you will be, and it's just free points all the time if you know all of these by heart. Okay. Okay. And then the only other example he gives of coenzymes, he talks about endogenously produced, so internally produced sulfur containing fatty acids. Yeah, our B vitamins are our big ones that we'll talk about all the time. Okay. Enzyme classifications, along with examples. So oxidoreductase. I feel like we've heard oxidation reduction reactions before, right? So what do we think that an oxidoreductase enzyme does?
Loss and gain of electrons.
Loss and gain of electrons are oxidation reduction reactions. Okay. A couple of the examples that he gives is like ethanol to aldehyde. And then like he also likes ethyl alcohol to acetic acid. Yay, autocorrect. Perfect. Those are the 2 big examples that he gives. Also, if we look above, we talked about this as well when the oxidation reduction reaction chunk way up yonder, wherever it is. We talk about the primary alcohol, secondary alcohol. Here it is. Primary alcohols oxidize, aldehydes are oxidized, carboxylic acids, aldehydes, all of these things, the ketones and the aldehydes. Know those guys, because he loves to talk about ketones and aldehydes. He loves it. Those ones. All the way back down. Wow, we're going through a lot of stuff. Transferase. What do we think these ones do? They transfer functional groups. So they'll transfer a functional group from one to another. The example that he gives, when we have glucose, change to glucose 6-phosphate. Let me actually pull up a. Look at this. So glucose to glucose 6-phosphate. This functional group right here, PO4. It's transferred from the ATP. ATP gets broken down, and it literally the transferase enzyme sticks that phosphate, this phosphatase group, from the ATP onto the glucose and makes it glucose 6-phosphate. It transfers it. And that is our transferase reaction. Hydrolase. This is, we talked about hydro before, hydrolysis. Hydrolysis of a substrate or breaking of a chemical bond using water to create products. So one example of this is our peptide bonds are broken or hydrolyzed by water. This is talking about the same thing as a hydration reaction. So any of like the splitting of a polypeptide chain. Really, if you see something where water is involved and it's breaking bonds, it's a hydrolase enzyme. Whenever we talk about enzymes, make sure you recognize this right here, this ACE. Every single enzyme ends in ACE. If it does not have ACE, it is not an enzyme. So he'll ask you questions like, which of the following is an enzyme that does whatever? And look at the answer choices, and most of the time, like 2 of the answer choices won't even have ACE on the end, and you immediately know, oh, those aren't enzymes, so that cannot be the answer. Okay, so lyase, ly as in lysis, as in breaking of bonds. So this is literally breaking of any chemical bond without the use of water. Someone's like it's CC, CO, CN, CS bonds. Yeah. Those kind of bonds will we use for that. It's yeah, that's about it. That's all you need to know. One example I use is fumarate to L-maltate. Don't worry too much about this. This is Krebs cycle stuff, which is it's either the very end of this try or the beginning of next try. I think it's at the very end of this try. Isomerase. We've seen the word isomer before, right? What's the isomer?
Same something.
So it's the same chemical formula, chemical makeup, just rearranged. Or same chemical makeup, but a different order. So essentially, like the bonds are placed in different places. So it's like if you were to have C2H6 or something like that, you can have it arranged in different ways where they're technically different molecules. They're isomers of each other. The same chemical formula, but bonded differently. Okay, so isomers of each other. So the isomerase is a transfer of groups within the same molecule to form isomeric forms. An example that he is dihydroxyacetone phosphate. These examples are just the ones that he uses in the book. So aldehyde 3-phosphate. Ligase. So if we had lyase, which is breaking down bonds, ligase is making bonds. And this is through condensation. coupled to a cleavage or breakdown of ATP or some similar coenzyme. Okay. Just understand like what each of these do, and so you'll see that as we get into enzymes, you'll see like a lot of the enzyme names are literally going to be like dihydroxyoxidoreductase. Like that's how they name the enzymes. So it'll almost tell you what it's acting on and what it's actually doing, what its function is. So if you know like what these mean and what they're like, what process they're doing, you'll have a much easier time understanding what the function of those enzymes are in the future. What is an active site of an enzyme where the substrate binds to it for the reaction? What is meant by substrate specificity of an enzyme? Big concept here. You'll have several questions on this. Each enzyme will bind to one specific substrate. Okay. That's what specificity is. The enzymes like specific substrates. In general, enzyme-substrate interactions. So just in general, the substrates bind to enzymes, forming what's called an enzyme-substrate complex. And then you'll have some kind of intermediate. We'll join. An intermediate is just like, if I remember right, it's just like any other kind of chemical. Like you can think of like the different coenzymes and stuff will act as intermediates as well. And those are going to join and products will be formed. Now we get into like the actual movement of it stuff. This is kind of transition state. So this beautiful chart, our substrates start out what's called the ground state, this S ground state or the substrate ground state. You can think of it as this is their energy level, like how much potential energy that specific substrate holds. Then we have what's called activation energy. So it's the amount of activation energy is the amount of energy that we need to put into those substrates to get them to actually react and to change to become products. Okay. Yeah, I don't want to go too much deeper into that because as you keep going, it starts to get a little bit more confusing. But the point is like this is what the normal reaction looks like. Do I have one of the? I don't have one with. Let's do the. Just grab one. Yeah. Here's another one. So when there's a when there is an enzyme, the catalyst, it cuts down the amount of activation energy needed to form the products. Okay. Catalytic strategies. For sake of time, because I really want to get down to the K, M, and V max stuff, I'm just going to, there's 3 different types. There's acid-base, catalysis, covalent, lysis, and metal ion lysis. Take a little bit of time just to Google those and see what those are. The effects of the following on enzymatic activities. So pH, each enzyme has an optimal pH at which it functions. If it goes above or below that, it doesn't work properly. Same thing for temperature. They have an optimal temperature. And if they go above or below that, they don't work as well. Substrate concentration. Higher concentration means more likely a reaction is going to take place. So if we have a higher concentration of our reactants, it is more likely that the enzymes are going to interact and for a reaction to occur. An activator is a chemical that will make the enzyme activate and go forward, do its job. And an inhibitor will stop the reaction from happening. That can be reversible, which just stops it for a certain period of time to help manage it, or irreversible, which means once it binds, never letting go, and that enzyme is essentially dead. The enzyme can no longer work. Let me see this later on. Yeah, we'll talk about this down here. Okay. Know the Michaelis-Menten equation of enzyme kinetics. Remember, this is all of our Vmax, VO, all that sort of stuff. Is this sort of the material that you guys are like, what the heck is this going on?
Yes.
I figured. Let me. I want to find the very good. There's a good graph. Okay, I can't find that graph, but I'll see if I can. Okay. So the Michaelis-Menten equation of enzyme kinetics. What we're talking about here is the rate at which reactions occur with enzymes, okay? So we're talking about how quickly the enzymes are working and how quickly the reaction happens. Okay, that's what this equation is referring to, okay? So the job of this equation is going to relate what we call the initial reaction rate, which is represented by V naught. It's like a, I can't do, well, let me do like little subscripts on here for some reason. Insert, I can't find it. It'll be a V naught. Usually like the zero is, it's kind of below the V, more like a subscript. So it's comparing, so it's relating that initial reaction rate. So when you very first put the chemicals, put the enzymes and the substrates together, right? The maximum reaction rate, which is our Vmax. So this is the maximum speed at which that reaction can be taking place. The maximum rate of that reaction is occurring, okay? And that correlates it to the initial, or the starting substrate concentration, which is S. Okay. These little brackets, if you ever see those mean concentration. So what's most important about this equation is understanding how it changes, okay? Which we'll get into two parts. Make sure that I keep this simple enough. You guys make sure it's understandable. Okay. First of all, does this part make sense? That we're relating that it's It's talking about the rate at which reactions occur with enzymes, and that we're relating the initial reaction rate, the maximum reaction rate, and the starting substrate concentration. Does that make sense?
Yes.
Kinda, sorta. Okay. So the Michaelis constant, okay? Make sure. The Michaelis constant is Km, okay? Km is the amount of substrate needed so that the enzyme can function at half of its maximum velocity. Okay? So our maximum rate is our Vmax, so how quickly that enzyme can pump out that reaction. We're going to talk about a constant value that we find that's referencing half that speed. Okay? Okay. What do you see? So the graphs and the charts that we're looking at, let me find just the plain chart before we get into how things changes. Michaelis reaction charts. Come on, open. And I will say, I think I'll have to find it. There's a specific video. I might have it. I might actually have it. Let me find it. I think I have it in my board prep. It's here somewhere. Just I think I put the video in there. Dang it, I didn't. I have it somewhere. I'll see if I can find. There's a video that I really like. There's a video that I really like that I'll try and find for you guys and post that, so you can watch it. That kind of explains this a little bit further. I think what gets people the most is just that there's a lot of stuff going on here, and so it gets a little bit confusing. So to keep it really simple, don't worry a lot about all of the different numbers and all this stuff. Know the definitions, so that Km, you're talking about amount of substrate. That's what you want to remember for Km. And the equation itself, remember, I think he has it written in the book, but hey, Joe. Hi. But what we really, really want to know, what you guys are going to be asked questions on, are these down here. It's just how it changes. Okay. Competitive, uncompetitive, and mixed inhibition of enzyme activities. Do you guys feel okay with what those are, or do we need to go over those? I went over them pretty well in the video that I recorded for YouTube.
If you need to go, then we can go over the video. I mean, you've done quite a lot.
Yeah, I would just say with these, should be a chart.
You post tutoring videos on YouTube?
Yeah, I go through the whole book.
Okay. What was your YouTube channel?
It's DrakeDC.Tutoring.
Thank you.
So here, this right here, this is what we want to know about these. So we have 3 different types of inhibitors: competitive, uncompetitive, and mixed or non-competitive, okay? Competitive inhibitors are going to be similar shape and size to the normal substrate that the enzyme binds, okay? So essentially it competes to bind to that same exact spot, to that enzyme active site. Which means that if we have a competitive inhibitor introduced, less substrate can bind to the enzyme and less of the product is going to form. This right here, this is what we want to know. These are what we want to remember, okay? So if we have a competitive inhibitor, the Vmax is going to stay the same, but our Km increases. So what this means, with a competitive inhibitor, with a competitive inhibitor, we need more substrate to reach our Km, also known as 1/2 of Vmax. Because if we have something that's competing for the same binding site, the same substrate binding site, the only way to get that 1/2 of Vmax higher is to add a bunch more of the substrate. But our Vmax remains the same. An uncompetitive inhibitor means that it's not going to bind to the same active site, but it's going to bind on a separate site on the enzyme. Let me just write this down. So it binds at a separate site on the enzyme after the substrate is already bound to the active site. Prevents the substrate from prevents the enzyme from turning the substrate into products. Okay, so kind of pauses it there. The uncompetitive is going to decrease our Vmax and decrease our Km. Okay. Our mixed inhibition of enzyme activities. Just show you guys this one. They're going to bind at separate sites, but may bind either the free enzyme or the enzyme substrate complex. Vmax decreases and the Km is unchanged. So really, how the Vmax and the Km are how those change is really what you really want to know for these, because that's how he's going to ask the questions. You don't even necessarily have to fully understand this equation and everything that goes into it, because it is a little bit complex, and honestly it sucked reviewing it, and I still don't have the easiest time explaining. I can understand it in my head, but I can't really. It's a little bit difficult for me to explain. I don't feel like I have the full grasp on that yet.
Does this come back later in other chapters or other classes?
Boards and like a little bit in pharmacology and toxicology in Tri 5. So like not really, but like a little bit. if you remember these, like what happens to Vmax and Km, that's all you need to know. If you remember those. Okay. Okay. Yeah, if you remember those, until try 5, you're fine. So, only other thing, last two things on here. Irreversible inhibition of enzyme activities. Essentially, it's an inhibitor that, unlike these three, the competitive, uncompetitive, and mixed around competitive, that are reversible, these ones cannot be reversed. They bind on there and they are there forever. And that's why they're very, very dangerous. They disrupt a lot of stuff. It's like aspirin stops the cyclooxygenase enzyme that produces eicosanoids, and you'll learn next try. Eicosanoids turn into prostaglandins, which monitor our pain response. That's why aspirin is a pain reliever. Heavy metal poisoning, like too much lead or excessive calcium, mercury and sulfhydryl groups will do the same thing and mess with our enzymes. Just know those examples. And the last thing, allosteric effect. This is the same thing, referring to the same thing as the cooperative binding that we were talking about earlier. How the binding of a ligand to one side on a protein molecule is that it has another site of the protein is affected. Just like in the hemoglobin, and you can have a positive allosteric effect or a negative allosteric effect. So either it increases its affinity or decreases the affinity on another part of the molecule or another part of the protein when it binds. Yeah. Sorry that last part was a little bit rushed. There's a lot of stuff in here. Like I said, I have the video on this. It's actually, I recorded it in 3 different parts. Part 3 gets into this, and I even think I don't explain a lot of this in part. I talk about competitive, uncompetitive, and mixed, but I don't get into the KM or the Vmax. I literally just say go YouTube it, because there are some really, really good quick YouTube videos describing it that do a much better job than I do.
I literally can't handle him. He's the cutest. Yeah, if you'll just send that video then, and I just looked up on YouTube and Ninja Nerd has one too, so
What? That's the one. That's the
oh.
recommend. Watch Ninja Nerd.
Perfect. I'll send out a link that to everyone.
Yeah, literally, if you go and type in Ninja Nerd Michaelis mention, or whatever the name of the video is, like the KM or whatever. I think it's like a 20-minute video, but he dives into it and goes over everything, and he's fantastic. If he has a video on a subject, I guarantee you watching it will very much help you understand it. I love Ninja Nerd videos. Okay, guys. That was a cool 16 pages worth of information. How does everybody feel? I'm gonna go ahead and stop the recording now.
I'm about to go binge watch your YouTube.